Last time, we finished a bunch of stuff, and I think you guys would have been able to do up through, what, 22 on the homework set. We'll start with any questions from that, so if anybody has any questions from the homework set, be happy to deal with some of those to start. Yes, Delaney?
I have a question about writing in the homework.
Sure.
If I just add a page and write it as the business and that, there's no parent.
So let's look at Delaney's here, and I'll show you exactly what I see when I look at your page.
Okay.
So this is what I see from Delaney's. Now, I would appreciate it if you're doing this picture taking, if you can flip these so it's pointing the right direction.
How do I rotate?
So if you right click on it, oh, you can't see what I'm doing. Why didn't you guys say anything when I was acted like you're supposed to be able to see what I'm saying? Let me do this. Okay. So when I click on Delaney's notebook, this is what I see. So she has some book page copied in here, which is perfectly fine. She took a picture of her notebook and pasted it in. So if you right-click on this image, one of the options is rotate. And I think we want to go right 90 degrees. And if you click on that, it takes it a second to do it. But it rotated that image now, so it's right side up for me. And we'll do the same thing with the other one down here. Rotate right 90 degrees. And boom. Okay with that? And again, this is what I see when I look at Delaney's. That's fine. The only thing I would ask here, Delaney, is that when you named your tab here, or your page, will you name it with the sections? Like section 1.1, section 1.2. And you can put commas in between them, but it just makes it much easier for me to check if I know which sections am I looking for.
The picture is the whole section. And then I have in the picture the section.
Again, if you can put what sections is in this picture, that makes it easier for me.
So as the title page.
So the next homework check, I would not want you to add to this. I'd want you to start a new page.
Right.
And again, label whatever sections are going to be in that homework check.
Okay.
That just makes it easier for me when I'm skimming through your guys's to know what I'm really supposed to be looking for. If that makes any kind of sense?
Yeah.
Does that make sense to everybody, what I'm asking for? And hopefully that's not, again, we barely got anything in here, so hopefully it's not a big deal. And if you want to do, if you're doing things individually, like if you're doing one separate page for each section, that's fine, perfectly fine. Just please give me a label as to what I'm looking at when I click on it, because sometimes some people are really nice and neat and organized, and Delaney's work seemed fine, but some people are not as neat and organized, and it really helps if I know clicking on this, what am I really looking at, what am I really looking for? And if you just give me the section or sections that page in OneNote is corresponding to, that helps me enormously. Okay? And what she did there was fine, right? 1.1 through 1.6. That's perfectly clear what I'm looking at. That's good. Okay? So that was I guess, homework-ish related question. But probably some people were wondering the same thing, what do you see when you look at my notebook? And that's a decent thing to cover. What else do you guys have? Yes, hold on, I need to use names to practice. Caroline. 12. Sure. So 12 is asking me to find the range and write my answer in interval notation. So notice that 12 doesn't tell you how to come about or how to come up with that range. So you're free to use whatever method you'd like. So one way you could do this is you could recognize that from your Algebra 3-4 class that this looks like a square root function. And you know that a square root function in this form, the domain is h to positive infinity, and the range is either k to positive infinity, provided the leading coefficient is positive, or it's negative infinity up to k if that leading coefficient is negative. So you might have used that. That's a perfectly reasonable way to justify the range. So in this case, you notice the leading coefficient is 1 and the k is 2. So the range you could have just written as 2 to positive infinity, just from looking at the function. That's a reasonable way of going about and doing that, although it relied on you remembering this rule from last year, which maybe we did or maybe we didn't. It's been a long time, so if you forgot, that's okay. Alternatively, if I don't remember that rule, I would just look at the graph. So if I wanted to graph this, I'll click on my graphing calculator or open my graphing calculator. So I'm going to go y equals, and then square root x minus 3, and then I got to move my cursor outside the square root and do plus 2. And I'm going to just graph this on the standard window, so I'm going to do zoom standard. And there's my graph. So I have my graph starting here at this point, and then continuing on forever to the right and up. So because it's always going to the right and up, I know the end of my interval for the range is going to be positive infinity. I just have to figure out what this very beginning point is. And if I do that, I can look just reading off the grid. I can say, oh, I went 3 over and then 1, 2 up. So it's the point 3, 2. The 2 part of it, the coordinate 2, is the part that I care about for the range. And because there's actually a point that has 3, 2, it has that y coordinate of 2 on it, I know I'm using a bracket rather than a parenthesis. So either way of approaching that I think is perfectly appropriate. And depending on what you remembered from last year, quickly, I wouldn't have wanted you to spend like 20 minutes trying to remember that from last year. Like, just look at the graph. If you don't remember, it's okay. But yeah, I think that that's perfectly reasonable. Is that okay with you?
Yeah.
Uh-huh. Anybody else? Yes. Hold on. Julia. 18. Sure. It says use a function grapher, so that's a graphing calculator, to identify and classify all maximums and minimums. That's bad grammar. That should be maxima and minima. Round your answer to the nearest hundredth. Okay? So I'm going to go to my graphing calculator. I'm going to clear out what I had there. Then I'm going to do x times. And to get the absolute value in there, I can press the math button, go over to the number tab. See the tabs at the top? So you use your left and right arrows to move over. And there's the ABS command. So I'll press enter there, and it gives me the absolute value bars. And then I can just type in the 2x minus 1 and hit graph. So this is what it's giving me. The only place that there might be a maximum and minimum is hiding right here, that maybe I need to get zoomed in a little bit closer to see if there's actually anything going on there. Because it's so close to the x, or like so close to the x-axis there, it's hard to really tell. But initially, I can tell there's no global max or min because I have arrows pointing up and down, right? So I'm going to go, it looks like most of the action is happening maybe between negative 0.5 and positive 1. So I'm just going to zoom that in a little bit there. And then maybe just between negative 1 and positive 1 on the y. So I'm just making a little tiny window right near the x-axis. And there I can see I do have, when I zoom in there a little bit, I do have a local maximum and I do have a local minimum. Now that was tough to see initially, right? If you looked at the standard window, it's hard to see that that was there. You had to go, looked kind of flat there for a minute. Maybe there's something going on. Now to find those points precisely, I can press second and trace and use either the maximum or minimum command. let's say, for instance, I want to find that local maximum. So I'll use the maximum command. So I need to find somewhere left of that maximum. Well, that looks good. So I'll press enter. And then use my cursor to find somewhere right of that maximum. That looks good. I'll press enter. The guess doesn't matter, so just press enter wherever it is. So it says that maximum is rounded to the nearest hundredth, 0.25, comma, 0.13. I don't know if you can read this. If you can't read this, somebody please turn off or stand up and turn out the light. If at any point you can't read what's on the projector because it's too bright in the room, stand up and turn off the light. You don't need permission. You don't need to ask. Just do it, like Nike says, because it's important that you can see. And if you can't see what's on the screen, like, fix it. Right? Is everybody okay? Julia, does that feel 0.13? I know it's probably unlikely that you can read that from way back there, but that's what my calculator output. Rounded to 2 decimal places because it says round to the nearest hundredth. So, yeah, you're welcome. Anybody else? Okay, majokes. Moving on. Who else is tired? This has been a long week. Wednesday felt like Friday to me, which means that it was a 7-day week, work week, which is rough, right? I'm making jokes, guys. Nobody's laughing. I can't even tell people if people are smiling or not because of these stupid masks. All right. Section 1.6 is about asymptotes. And we know what an asymptote is, right? It's a line that the graph approaches but does not cross. You remember that from last year? Okay. And we know there's a couple different kinds of asymptotes. Specifically, we spent a lot of time probably talking about horizontal asymptotes and vertical asymptotes, right? Now, for the sake of simplicity, when we refer to horizontal asymptotes, we're still going to refer to things like the following. So let's say we have y equals 3x, or x squared plus 3x minus 3 over x squared plus 2x minus 3. And I'm going to graph this in Graphmatica because it's a little bit easier to get a picture that's going to go good in my notes. But your graphing calculator will graph this just fine also. So let me do that. And I have vertical asymptote here, and here, and a horizontal thing here. Let me do this and get those grid lines out of there. I'll make this a dashed, this a dashed, this dashed, and let me make this one purple, and we'll make all of these guys the same color. Oops. How nifty is this, right? I just took like a minute to make a pretty primo looking graph here. Not too shabby, right? All right. Well, nobody's impressed today. You guys are a tough audience. Is it just Friday or is it me?
Friday.
Okay. Fair enough. I'll try to be funnier. So if we look at this, it's pretty clear that these guys are vertical asymptotes, right? No ambiguity there. This guy, we're going to refer to a horizontal asymptote, or refer to as a horizontal asymptote, even though what do you notice is happening? The graph crosses it here, right? Technically speaking, we would refer to this just as an end behavior rather than an asymptote. The end behavior is like the weaker condition. Both asymptotes and end behaviors, the end of the graph follow the asymptote. But the end behavior, you can maybe cross in the middle, which is what's going on here. But for the sake of simplicity, we're going to just refer to these situations as horizontal asymptotes, even though it makes my skin crawl to do so. Nobody thinks none of this is funny. Goodness gracious. Okay. Well, we'll keep on going here. One way to detect something as a horizontal asymptote, even though like it looks like that's what's going on visually, right? You can test this a little bit more with our calculator. So one way we might test this is if I go and I type in my function here. Do you guys know the fraction shortcut on your graphing calculator? So if you press the alpha button and then the y equals anywhere on an input screen, it's going to open up this fractions menu. And I can choose this numerator over denominator option. And it puts like the fraction bar in there, so I can type these rational functions exactly like they look on my sheet of paper. I think it makes life a little bit easier to deal with things. If I'm able to do that. I think that was the function. Let me turn back my notes and make sure. Oh, no. That should be a plus 2x. Crisis averted, though. Okay. So what I'm going to do is I'm going to use the table function here to check this. And really what I'm going to be doing is I want to look at the value of y as x gets bigger and bigger and bigger, right? That'll tell me whether that y equals 1 is actually an asymptote or not. So I could scroll, but that's really unsatisfying because it's taken me a long time to get to big values of y or big values of x. Instead, if I press second in the window and open up the table set button, this first option, the table start, would allow me to like skip to x equals 100, which is a pretty good deal, so I don't have to go press the down arrow like 100 times. So when x is equal to 100, y is getting pretty darn close to 1. And as I continue to get closer and closer and closer, or further down, further and further away, that y value is getting closer and closer and closer to 1, right? You see that there's some fractions thrown in here. So that's the one downside of using that fraction shortcut, is that the calculator then wants to output everything as a fraction when possible. Sometimes the fractions are too big for its memory and it defaults to a decimal approximation. But that's what's going on here, why I have like this 5,165 over 5,125. Because I wrote this thing as a fraction, it's giving me a fraction as an output whenever possible. That's the downside of it. The upside is you get a really nice looking graph. But you can't see it because I'm on that old stupid window. I just violated my own rule of using zoom standard instead of pressing graph. Ugh. Is everybody okay with that idea? So you can test if something's actually an asymptote by just looking at progressively bigger and bigger values of x and checking to make sure the values get closer and closer to that asymptote without actually jumping on the other side of it or whatever. And same thing, you'd want to check the smaller and smaller values of x. Everybody's okay with that? Now in practice, we know how to find the asymptotes for rational functions from last year, right? For either a general rational function or a simple rational function, you can find the vertical asymptote by setting the denominator equal to 0 and solving. And remember, for a simple rational function, this was something of the form like this. Or I guess we also had a form where it was like a degree 1 polynomial over another degree 1 polynomial with nothing added to it afterwards. Those are both things that we'd call a simple rational function. A general rational function means that at least one of the numerator or denominator is a degree 2 polynomial, or better, degree 2 or higher polynomial. So like if you had a degree 1 over a degree 2 polynomial, that's a general rational function, as opposed to a simple. The horizontal asymptotes, then, for a simple rational function in this form, it's just y equals k, right? You guys remember that? For a general rational function, it was a little bit trickier. So you had 3 cases. The first case, when the degree of the numerator is less than the degree of the denominator, you had asymptote or end behavior, but in this class, or this situation, we're just calling it an asymptote at y equals 0. If here the degrees were equal, the asymptote is at the leading coefficient of the numerator over the leading coefficient of the denominator. And 3, if the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. You have that slant asymptote instead, or oblique asymptote. I don't know what vocabulary you used last year, but you could refer to it either way. So again, we had these rules for rational functions from last year. Do these ring a bell? Look familiar? Okay. Again, if something isn't familiar and you need, like, can we really have some more explanation on something like this, I'm happy to do that. But these things that I assume that you did last year and we kind of remember, and I don't need you to like have perfect memory of it, but just like need to recognize it, like, okay, yeah, I remember that was a thing. That's the rule. Okay, I'm good with that. If you're not, please say something. We'll, I can be more specific and we can do some more example and really kind of talk some more about it, but I don't want to like go and reteach things that you already kind of remember and are like tremendously bored by me doing that. Okay? So again, like I'm motoring through some stuff here, and if you're like horribly confused, please stop me and say, like, I'm horribly confused. What the heck are we talking about right now? And I am happy to slow down and like go into more detail, but if we're all good, I'll continue to motor. But I figure I should stop and give that disclaimer here, since everybody looks just pretty beat down from 5 days of school. So I don't know if it's because feel like everything is hopeless or just that we're tired. So I figured I'd stop and let you guys know that you can stop me if I get going and start assuming things that you won't, assuming that you know things or have seen things that you haven't. Okay? Okay, so we have those rules. So for example, let's say f of x is equal to 3x over x plus 1. What would the vertical asymptote be in this case? Anybody? -1, right? How did you get that? You said x plus 1 equal to 0 and solved, right? And what would the horizontal asymptote be in this case? It's going to be y equals 3. Why 3? Well, I have a degree 1 polynomial over a degree 1 polynomial. So the horizontal asymptote is going to be the leading coefficient over the leading coefficient. In this case, 3 over 1. Everybody's okay there? Okay. And you could then test your assumption by looking at the graph and even making a table of values if you really weren't sure about the horizontal. Is that okay? Okay. The next section, 1.7, this will be the last section we cover today, by the way. It's kind of long. And if I don't actually end up finishing it, that's okay. But this will be, even if I do finish, this is going to be where I stop, is at the end of this section. One way or the other. Okay? All right. Fair enough. Okay. So we're going to start by just reviewing a couple of the fundamental operations on two functions. Let f and g be two functions with intersecting domains. Then, for all values of x in their codomain, the algebraic operations performed on f and g are defined as, and then I'll get ready to write some rules here in a second. But before I write these rules, I want to ask a couple of kind of questions here, just to think about things. So, we have the condition that f and g have to be functions with intersecting domains. What do we mean by intersecting domains? So let's ask a different question then. Let's say the domain for f is the interval 3 to 5. And the domain for g is the interval 2 to 8. Are these intersecting domains? What do you guys think? Yes. Why would you say yes?
Part of the function, like within the function overall.
Yeah, there's stuff that's in both of the two domains, right? For example, the number 3 is in both of these two domains. Is everybody okay with that idea? With what we mean by intersecting? It means they have to have stuff in common. Why is that important? What if they had no stuff in common? Could you combine them together? No, right? What would you get as an answer? For any kind of operation you could do if they had nothing in common. The answer for everything would be undefined, right? For example, if we had this G and F, if I did F of -3 plus G of -3, this is undefined, right? Because -3 is not in the domain for G. And if you add something to undefined, what do you get? Still undefined, right? Undefined is like the killer. It just makes everything else undefined when you run into something like that. So this is just this condition that F and G have to have intersecting domains just makes it possible to be able to even do a function operation without getting undefined as your answer. That's all that condition is there for. Is everybody okay with that idea? Okay. So, a couple of rules. So how do I evaluate the sum of, or the sum of two functions is the same as the sum of those individual functions? Hopefully that's not very surprising. Everybody's okay there? What about the difference of two functions? Well, that's still just the difference of the two individual functions. How about the product of two functions? Well, again, that's just the product of the individuals. And the quotient is just the quotient of the two individual functions provided on one condition. That is that g of x is non-zero. So for example, if f of x is 2x minus 3, and g of x is the square root of x plus 2, what is f plus g of x equal to? Well, from my rule above, I know that's the same thing as f of x plus g of x, right? And I know that f of x is just 2x minus 3. And I know that g of x is just the square root of x plus 2. So I'll make those substitutions. And then I would try to combine any like terms here, since all we're doing is adding two things together. Are there any like terms to combine? No. So what do? We circle that as our answer because we're done. That's all we could do. Rather dull, but we did it. What if we wanted to do g minus f of x? Well, I know that g minus f of x is just going to be g of x minus f of x. And I know g of x is the square root of x plus 2. And f of x is 2x minus 3. But this is not right, what I've written down. What's wrong with this? Daniel, is that a hand or no?
Yeah, it's fine. That's all I need.
Okay, you can factor out a negative, but that's true, but there's an issue even with what I've written down here before we try to do anything else. What I've written down here is incorrect. Not because there's more we can do, but because I fundamentally, that the previous step isn't actually equal to this step. Can anybody see the problem? Yes, Pablo. I couldn't hear what you said. Pedro, I'm sorry. It's on my sheet, correct. I'm stupid. Right. So that means that the negative sign needs to apply to the entire f of x. So what I should have written down instead really should have been minus 2x plus 3. Everybody see that? Very easy place that students make mistakes. When we substitute a function in, when there's a negative sign in front of it, we have to make sure that negative sign applies to all the terms of that function. Very easy to forget to do that. In fact, so easy to forget to do that when I wrote it down wrong, we all sat here like, I don't know what's wrong with that. That seems right. It's very easy to make that mistake, which is why this is included in the examples, just to remind you guys about this. But now that you've seen it, you know to be on the lookout. And I know nobody will make that mistake now, because you guys all have perfect memory and attention spans. Okay, g times g of x. Well, again, if I use my definition from before, that's just going to be g of x times g of x. And g of x is the square root of x plus 2. Everybody's okay there? What's the square root of x plus 2 times the square root of x plus 2? X plus 2? Does anybody disagree with that? So this is what's written in my lessons, but I would disagree with this result. Why would I say there's an issue with that? I would say there should be an absolute value sign around this. Let's think about why. Because we can't have a negative. Why can't we get a negative out of this? So these has to be a non-negative, right? Because each of those are square root functions. You can't get a negative to come out of a square root function, right? If I multiply two non-negatives together, I better be getting something else that's non-negative, right? So I really think you should have an absolute value around that. As an aside, maybe you remember that one definition for the absolute value that we used was this. Oops, usually write it the other way though. The square root of x squared. Do you remember that? Maybe. I don't know. because you're guaranteed to get a positive result from that also, right? Okay. Nobody's excited about this stuff today. Man. Fridays are the pits. Until 2:45, and then it's like the greatest day ever. Or maybe like 4:30 if you have practice also after school. Well, maybe you look forward to practice. I don't know. No? Nobody does? That's not a thing? Okay. So again, using our rule from above, f over g of x is f of x over g of x. So I have 2x minus 3, but that's not really much of a 2, over square root of x plus 2. And I'm okay with stopping here, even though like you could rationalize that denominator or whatever and get the square root out of there. But I would tell you that when the stuff underneath the square root is a polynomial, I don't need you to rationalize the denominator. As opposed to like 1 over the square root of 2, I would expect you to rationalize that denominator. Because the only thing in the denominator is constants. Is everybody okay with that in terms of like a general simplifying rule for me? If the stuff under the square root is a polynomial, has any x's in it at all, don't bother rationalizing the denominator. But if you have just numbers, we'd kind of expect you to rationalize the denominator there. Unless we tell you not to. So those are the first 4 basic function operations. There's a 5th one, though, called composition, which, again, I think you touched on last year. And what composition says is that f compose g of x is equal to f of g of x. So remember the composition symbol is basically like that multiplication dot, but it's an open circle instead of a filled in circle. And we read that as f compose g, not fog. Please don't read it as fog. It just bothers me. It's not an O. It's a little dot with an open circle in it. So let's review how we do composition here real quick. So let's just do a couple of examples here. Okay, so f of x is 2x squared minus 3x, and g of x is negative 3x plus 4. So I know that my definition for composition says that this is equal to f of g of x, and I substitute in my g of x. And then what this function notation says is that in my function f, everywhere there's an x, I'm going to replace that with a negative 3x plus 4. So I'm going to have the 2, but instead of x squared, I'm going to have negative 3x plus 4 squared. And then I'll have minus 3 times, but instead of x, I'm going to have negative 3x plus 4. You guys remember doing that last semester, last year? This would have been a first semester thing, right? No? I don't know. I don't remember when you do it. Is it second semester? I should remember. I'm teaching that course this year. So I better remember sometime. Okay, so this negative 3x plus 4 squared is just 9x squared plus 16, right? No! Should have gotten a stronger result from you guys. What do I need to do here? Foil it. Yeah. So I'm going to do the foiling in my head. I hope you don't mind. That didn't look like 16 to me. And then we just distribute the other place. Everybody okay here? And then we'll distribute the 2. And then we'll combine like terms. And there's my answer. So, took a minute. We'll do another. This time we'll do the reverse. G compose F. So that's just the same thing as G of f of x. And the first thing that I'm going to do is I'm just going to substitute in f of x, or the expression for f of x in its spot. And now what the function notation tells me is that I'm going g of 2x squared minus 3x. Everywhere in g of x there was an x. I'm going to replace it with a 2x squared minus 3x. So negative 3, but instead of my x, I'm going to write 2x squared minus 3x, and then I have the plus 4. And oh, this is so much nicer because look, there's no foiling to do. I can just distribute the negative 3. And there's not even any like terms to combine, so I'm done. Look at examples A and B. What do you notice? Those are not the same thing, right? F compose G is not the same as G compose F. We got two different answers, right? Up until this point, this is the only operation that you've seen that's not commutative. By that means you can do it either direction and get the same result. Everybody okay with that idea? Right? If you add two numbers, it doesn't matter if you do 2 plus 3 or 3 plus 2, you get the same thing. Did you guys do matrices last year? Matrix multiplication, also not commutative, right? Matrix A times matrix B could be different from matrix B times matrix A, right? Even if you narrow it down so that both matrices A and B are square matrices, still doesn't hold. Or even if the dimensions match up to make the multiplication possible and get the same dimension result, you still aren't guaranteed to get, or still aren't guaranteed commutativity. Anyways, so order matters there a lot. Last year in your Algebra 3-4 course, the reason we defined the inverse was, or the reason we defined composition is so that we can use it for this theorem. We say that two functions, f and g, are inverses if and only if g compose f of x equals f compose g of x which is also equal to x. What is this really saying? It's saying that f and g basically just cancel each other out, leaving you with whatever the original input was, in this case, x. So just like adding by 2 and subtracting by 2 would be inverse functions, if you take a number, you add 2, and then you subtract 2, you have the original number again, right? That's the idea. So let's do some examples of finding inverses. So if we have a mapping diagram, and we call this function f of x. Number one, quickly, how can I look at this mapping diagram and tell that f is a function? Good. So all the x's are used, right? And they all just go to a single location, right? No x is going to multiple places. So if I wanted to find the inverse then, what would the inverse, let's write over here. What would the inverse of f of x look like? What would its domain contain? Contain 4, 5, 6. And what would its range contain? 1, 2, 3. Where would 4 have to go to? Have to go back to 1. Where would 5 have to go to? Back to 3. And where would 6 have to go to? Back to 2. So what are we doing here when we find an inverse from a mapping diagram? We're basically just reversing all the directions, right? We swap the domain and range and everything, and we just reverse the arrows. Everybody okay with that idea? Okay. Of course. What if we have a set of ordered pairs? Oops. Let me call this f of x. What's the inverse for this function got to be? What's the first ordered pair got to be in this inverse? I'll do it for you guys then. Should be 4, negative 2. What would the next ordered pair be? Go ahead. Excellent. And then the next one? 8, 3. Very good. And the last one? 8, 5. What are we really doing here to find the inverse? Just swapping the x and y coordinates, right? That's all we did. Everybody's okay with that? Okay, go back and look up at example B. F of x was a function. Was f inverse a function? Yes, right? Everything in the domain is used and they each go to one place. Let's look at part B. F of x is a function here. Is the inverse a function? No, why not? The x value of 8 is going to two different locations, right? So sometimes the inverse is a function, and sometimes it's not. Is there going to be a way to predict when the inverse will be a function? Yup. But we need some definitions first. So the first definition we're going to do is for a term called onto. And some places call onto surjective, depending on the textbook you're looking at. They're probably used in equal measure, those two terms. If every element in the range is mapped to by some element in the range or in the domain. So basically we're saying all of the ranges are used. Everybody's okay with that? A function is called one-to-one or injective. Again, different textbooks call them one-to-one and some call them injective. They're probably done in equal measure. If every element in the domain maps uniquely to distinct elements in the range. So what do we mean there? We mean that the y values are used only once. And we say that a function is bijective if it's both one-to-one and onto. So, with these definitions, we have the theorem that f inverse of x is a function if and only if f of x is bijective. Let's go back and look at those previous two functions and where one was an inverse and one inverse was a function and the other inverse was not, and go look at the original, the f of x functions, and see if we can tell if they're, which part, if it passes both parts or if it fails both parts. So looking at this example A, if I look at f of x, all the ranges got used, right? Everybody agree with that? They all have an arrow going to them. So we have onto. Each of the y values is used just one time. So we know it's 1-to-1. Those two things together guarantee that f inverse is a function. Everybody's okay with that idea? Let's look at example B. So the range here would just be 4, 6, 8. All of them are used, so we have onto. However, the y-coordinate of 8 is used twice, so we are not 1-to-1. If the function isn't 1-to-1, when we make the inverse, those repeated y-coordinates turn into repeated x-coordinates, and that's why we'd fail to be a function. That's why the 1-to-1-ness is necessary. Is that okay? What would happen if we weren't onto? What part of the function definition would fail for the inverse there? Exactly. Very good. So if f of x is not onto, we'd have some y that wasn't paired to an x, right? So when we swap the x's and y's, when we make our inverse, that unpaired y becomes an unpaired x. And you can't have a function if you have an x that doesn't have a partner, right? So you need both 1-to-1 and onto to guarantee that the inverse is a function. Okay. Let's do some more finding the inverse. Oops. So here's our function for f of x. So if I want to find the inverse for this, what I'll do is I'll just transpose the x and y coordinates and draw my new graph. So 0, -3 becomes -3, 0. 1, -1 becomes -1, 1. And -2, 5 becomes 5, -2. So if I draw my graph now, there's f inverse of x. Is everybody okay with that idea? Is f inverse a function? No. Right? It fails a vertical line test, right? So what part of the 1-to-1 or onto did f of x fail? It's not 1-to-1, right? There's lots of y values that have two different x values associated with it, right? This would be like 2, 5 over here. You see? So, what is a reasonable test for 1-to-1-ness? Yeah, a horizontal line test. Exactly right. So if you have a graph, you can check to see if the function is 1-to-1 by using a horizontal line test. If that horizontal line intersects the function more than once, it's not 1-to-1. And immediately you can say then that its inverse will not be a function either. Right? That's a direct consequence of not being 1-to-1. Okay. We have 2 more examples and we're finished for today. So hold in there, guys. You've been mighty good sports. So to find an inverse algebraically, do you remember the 2 steps to do this? You did this last year. The first is to get x by itself. And then we swap the x and y. Do you remember that? Okay. So I'll just replace the f of x with a y. And then I'm basically just going to get the x by itself, so add 7 to both sides. And then divide by 3. And then we switch the x and y. And really, at that point, we'd rewrite it with the f inverse notation. Like that. Does that all look familiar? Okay. So we can say then that these 2 things are inverses, right? What if I asked you then to prove they are inverses? We have a theorem for this, right? If we go back to this right here. 2 functions, f and g, are inverses if and only if both compositions give you x. That's the tool that we're going to use to do this proof. So if we're asked to prove 2 things are inverses, that's what we have to do. So let's start doing f compose g. Well, maybe I'll call G F inverse, huh? Since I called it F inverse up there. So there's that. So F of anything, I'm going to plug that thing in for X. Is everybody okay with the composition? Any objectors? Okay. The times 3 and the divides by 3 cancels out. I can drop the parentheses, and the plus 7 and minus 7 cancel out. And I'm left with just x, which is what I wanted to have happen. Now let's do F inverse compose f of x. So that's the same thing as F inverse of x. So we'll replace f of x with 3x minus 7. And we'll just plug that into F inverse. So everywhere in F inverse there was an x. I'm going to write 3x plus 7, or 3x minus 7, excuse me. Everybody okay there with the composition? Now I notice there's no real reason that parenthesis needs to be there. So the negative 7 and the positive 7 cancel each other out. And then the times 3 and divides by 3 cancel each other out. And I'm left with just x, which is what I need. So we're done. And I'm done, and you're done, and everybody's done. And it's now